Hello everyone, this is going to be lecture 2 on abstract algebra. So in the previous class, we have done the basic definition of groups and have seen the properties of subgroup, and also seen the abelian groups that are like commutative. Like if you take any two elements from the group, that is A and B, such that we have A star B, or A to perform the binary operation in between A and B is equal to the binary operation between B and A. Okay, so this is what we have done in the previous class. Let us talk few more about the properties and examples of these properties. Let's see. So here we have the general linear group over R. That means what? If you have a set of all invertible 2 by 2 matrices, and the entries of these matrices are taken from R, this set is known as general linear group over R, and it is often denoted by GL2R. It is also a group under matrix multiplication. The identity matrix I2 is called the identity of GL2R, and if suppose we have A and B, for example, if we take two elements from GL2R, then we have if you want to find the inverse of this matrix, so the inverse will be equal to B inverse A inverse. How do we prove it? We can prove it in this way: AB into B inverse A inverse. So the B inverse get cancelled, gives us identity. A into A inverse will give us identity. So from here we can say that the inverse of AB is B inverse A inverse. Similarly, in the same way, we can show the left-handed inverse as well. So this was the right-handed inverse we have shown. In the similar way, we can show the left-handed inverse, that is B inverse A inverse. When it gets multiplied by AB, it will give us our identity matrix. Now from here we can say that the matrix, that means the closure is there. So we are doing what? We are taking the set of all 2 by 2 matrices, and we are taking the invertible matrix, and the group operation we are defining is matrix multiplication. That means what? We are taking the matrices of the type this, and we are defining the operation, of the binary operation we are defining is matrix multiplication. So what is the condition we have that the matrix is in this set? Is that the matrix has to be 2 by 2. The order of the matrix should be 2 by 2. And the matrix has to be invertible. Okay. So for that case, suppose we want to show that this binary operation is closed. That means what? The operation we are defining, the closure is there. So that means what? If we want to multiply two matrices, and if you want to check that the resultant matrix is suppose C, and that matrix belongs to our set. So what is the set? We have the set name of the set is GL2R. So we must need to check whether the inverse of this matrix C belongs to our set or not. So for that, we want to find the inverse. So in order to find the inverse of C, we want to find the inverse of AB, right? So we can see that if we multiply AB by B inverse into A inverse, so that means what? Since the matrix multiplication is associative, we have read in our basic classes. So from here we have what? The BB inverse get cancelled, we get A multiplied by A inverse, which will give us our identity matrix. Similarly, we can show the left-handed inverse as well. So from here, we can show that the matrix AB is invertible. So for that, we can say that the matrix multiplication group we are defining, it is closed under multiplication. Now, we also know that the matrix multiplication is associative. That means what? If we are multiplying three matrices, we can multiply the second two first and then multiply with the first one. And this will be equal to if we multiply the first two and then multiply with the second, okay? So this is how we can say that the matrix multiplication is associative. Now, since we have taken the group of all the elements which are invertible. So if we want to satisfy the third property, we can say that every element of this 2 by 2 matrices or the GL2R group has an inverse. For example, if we want to find the inverse of A inverse, we can simply take the inverse, which will already give us the matrix A, right? So that means what? If A belongs to GL2R, that means what? If the matrix A has an inverse in R, then the matrix A inverse will also be having an inverse. Okay, so it's a very basic thing to know. now the thing we have that from here we have satisfied the four properties. So what are the first property? We have satisfied the closure from here. The second property we have satisfied is the associativity property. The third one we have shown to be the inverse property. And we also know that the identity will be what? I2, that is what? 1, 0, 0, 1 is the identity. That means what? No matter whatever matrix we multiply by the identity of order 2 will give us the matrix A, right? So from here, all the four properties of the groups are satisfied. And hence, we can say that GN2R is a group. Now we want to check whether the group is abelian or not. So in order to check whether the group is abelian or not, we need to check whether matrix multiplication is commutative or not. So this is a very basic example because we have already seen, because we are dealing with matrix from very young age, we have seen that matrix multiplication is not commutative, right? It satisfies all the other properties, but multiplication is not commutative. So here they have given a basic example. That means what? If you multiply this matrix 1, 1, 0, 1 with this matrix, you get this matrix. Similarly, if you change the order, change the way we are doing the matrix multiplication, you get the other matrix. That means what? This matrix multiplication is not abelian. So from here we can say that this is a non-abelian group. Okay, that means what? The set of all invertible 2 by 2 matrices over R, it forms a group, but the group is not abelian. Okay. Similarly, the group we have defined is over the entries of R. We can change the entries of the matrix and we can found a group which is defined on the entries over Q. Okay, so we can define that we can change the entries of the matrix to Q as well, and we can find another GL to Q group. Okay, now the next type of group we have is the symmetric group. So the symmetric group is what? We take a set of numbers, like suppose we take the set to be 1, 2, 3. And we want to consider how many permutations we can have on it. That means how many way we can rearrange these numbers, right? For example, if you want to apply the permutation sigma, which does what? Which takes the number 1. So that means what? We have the numbers 1, 2, 3, and we are defining the permutation sigma, which does what? Which takes the number 1 to the number 2, number 2 to 1, and number 3 to itself. Okay, this is one permutation we can have. Similarly, we can do what? We can have, in this way, we can have 6 permutations, right? We can simply derive it from the formula of permutation, that the basic permutations we can define is 6 type of permutation we can define on this. And there are 3 choices for sigma 1. In sigma 1, where we can first we can have that the function or the permutation sigma we are defining, it does what? It takes the 1 to the number 2. It takes number sigma 1 to 2, and then sigma 2 has what? So that means what? Sigma 1, that means what? Number 1 has 3 of the choices, that is 1, 2, 3. Number 1 can go to 1, 2, or 3. So the number 1 is having 3 choices. Similarly, when the number 1's choice is fixed, the number 2 have the choice of the other 2, right? So it has 2 other choice, and when the choice of 2 is fixed, 3 is having only a remaining 1 choice for it. So in this way, we can say the number of permutation we can have is 6 permutations. Okay, so this is a very basic definition of symmetric group. We will look into the properties of it as well. Okay, for example, if you look into it like 1, 2, 3, so the 1 in the basic notation, when we are defining the symmetric group, we write it in this way only. So the one element goes to the element 2, the second element goes to the element 1, and third element goes to the element 3. So if we want to define the complete set of permutations, we have that the first kind we have is the identity permutation. It does what? It takes all the elements to itself. So the 1 goes to 1, 2 goes to 2, and 3 goes to 3. This is also known as the identity permutation. The second one we have is the element 1 is fixed, but the 2 goes to 3 and 3 goes to 2. For the third one we have that the element 3 is fixed, 1 goes to 2 and 2 goes to 1. In this, not one element is fixed. So 1 goes to 2, 2 goes to 3, and 3 goes to 1. Similarly, we can define this one and this one. So from here, we can say we are having a total 6 permutations. Now, if you want to discuss the composition of permutation, that means what? If we apply 2 permutations, one after the one. For instance, first we apply the tau permutation, then we apply the sigma permutation. This is known as the composition of permutation. So it will be equal to what? First, we apply the tau. So we want to find tau of 1. Tau of 1 is what? 3. So first we apply the tau of 1, then we apply the sigma of tau of 1. That will give us sigma of 3. The sigma of 3 is what? It is 3. So in this way, we can define the composition. Similarly, if you want to find that sigma composition tau of 2, so first we will do what? First we found tau of 2, which will give us 1, right? So tau of 2 is 1. And that sigma of 1 is what? 3, right? Sigma of 1 is 2, right? So then we have the sigma of 1 to be 2. Now, if you want to find sigma composition tau of 3, so tau of 3 is what? 2. So we have sigma of 2 and that is 1. So the composition thing is very easy. And if you want to find sigma dot tau, we find this element. And this element also is it is also a what? It is also a permutation on the set 1, 2, 3, right? So from here, we can say that the composition also is a closure property, right? Similarly, we can define the composition on Z and Zn as well. Now, if we move to the next one, let's see what properties we have. So from here, yeah, that's what I'm saying, that we can define the closure. That means what? If we take the composition of any two matrices, any two permutation, we get a permutation on that set only. So from here, we can say that the closure is defined. That means what? If we take any two permutations of A, of the set of all permutations on the 1, 2, 3, on the elements 1, 2, 3, the composition will also be another permutation on the set 1, 2, 3, right? Now we can also define the associativity. So the associativity is also defined. We can simply check whether the associativity is defined or not. Okay. Similarly, I have also told that this element is identity. So no matter whatever elements composition we take over with the identity, we get the same element sigma. Now, if you want to find the inverse, so the inverse has to be obtained in such a way that if we compose, suppose sigma is an element, and we want to find the inverse of the sigma. So let us say that the inverse of sigma is tau. So we must compose sigma with such an element tau such that it gives us the identity, right? So it is very easy to calculate. Suppose we want to find 1, 2, 3, 2, 3, 1. Now, if you want to find the inverse of this element is this, because we want to have to do what? We have to take the composition of all the elements and check which one is giving us identity. So if we take the inverse, if we compose these two elements, we get the identity. So from here, we can say that these two elements are inverse of each other. So from here, we have what? We can say that the existence of inverse is promised by the, is there for the permutation groups. Now, if we want to find the commutativity also, so if we check, if we take the composition of these two elements, we are getting this element. And if you get the composition of this, if you opposite the order and take the composition, we're getting the other element. So from here, we can say that the multiplication or the composition of two permutations is not a commutative, but it will form a group. That means what? It is a group, but it is not a abelian group. So till now, we have seen two groups, which are groups are there, but they are not abelians. First one we had is GL2R, which we have seen previous to this one. And this one is the set of all permutations. And the binary operation we are defining is the compositions of the operation. And the set of, and this group has a special name on it. So the set of all permutations we are taking. And if we are defining the composition, then this is known as symmetric group. And if we are taking three elements, it will be known as symmetric group of order 3, and it is defined by S3. Similarly, if we are taking the permutation groups on n elements, it will be defined by Sn. Okay. Now let us move to the next example. Okay, now we have some of the basic definitions. So suppose we have a group G and it is defined on the operation star. And suppose we have another group H on which we have defined this dot operation. That means what? We are having two different groups. Okay, so the G is a group with the operation star and H is a group where the binary operation we are having is dot. Now, if we want to define the Cartesian product of these two groups, that is G cross H, it will be defined by a new operation that is known as this diamond shape, which will give us G1 comma H1. So G1 comma H1 is what? The G1 is the element of the group G and H1 will be the element of the group G. And if we take the composition of these two elements with the other two elements of this group, so this G1 will compose with G2. And we know that what is the operation that is defined on the group G? It is a star operation. So we will get G1 star G2. And this H1 will get composed to H2. So we will get H1 dot H2, right? So this is how we can define a new group from the, if we are given two groups, okay, from there we can define this new group. And this group is also known as the direct product, okay. Now they are saying that the direct product, so till now we are not sure whether the direct product is a group or not. But if we check all the properties of this, we can say that the direct product, if we take the direct product of any two groups, the resultant set we are getting will also be a group. Okay. Now let's move to the next property. Because here is an example we are having. Suppose the first group we are taking is Z5. So what are the elements of Z5? It is the class 0, class 1, class 2, class 3 and class 4. But for simplicity, we do what? We write it as it is, that is 0, 1, 2, 3, 4. Okay, we write it in this way. And what is H? H is S3. So we have seen the elements of S3 as well, right? It is the symmetric group on the elements of permutation of three elements. So if you want to define G cross H, so the first element of the direct product we are taking is from the G, and the elements of G are 0, 1, 2, 3, 4. These are not the only elements, it's the class elements, okay? So the first class we are taking 4, and the second element of H we are taking is a permutation on H. Similarly, the second element is 3 and this. Now, if you want to define the composition, so on Z5, we know that which operation is defined on Z5. We have the addition operation we have defined, which forms a group. So for that, this 4 will add it to 3. So in the resultant element, we are getting 4 plus 3. So 4 plus 3 is what? 7, right? But since we are talking about Z5, so we will divide 7 by 5 and see that the remainder we are getting is 2. So this 7 will belongs to the 2 class. And then we find the composition of these two elements. So the composition is very easy. First, in order to find the image of 1, first we will check the second one. So 1 goes to 3. Now we will move to the first one and see where 3 goes. The 3 goes to 1. So from there we can say that the 1 goes to 1. Now we check the second element because we want to find the image of 2. So the 2 goes to 2. Now we go to the first one and see that 2 goes to 3. So the image of 2 will be 3. Now we will check for the third one. The 3 goes to 1. So if we go to the first one, the 1 goes to 2. So the image of 3 will be 2. Okay. So from here we can define the direct product, and it's a very easy and interesting concept. Okay. Now here we have the few properties. Suppose G is a group. So the first two properties are very important, that the identity elements in the group we are getting will be unique. Okay. So for all the elements in the group, the identity is unique. But if you talk about the inverse is unique up to the element. For example, if we change the element A1 from A to A1, we are changed. The inverse will also change to A1 inverse. So for a particular element, the inverse is unique. Okay. Now suppose G be a group and A and B are two elements in our group G. If you want to find this will be equal to what? A inverse of inverse will give us A. And this property is also known as sock and shoe property. Let me write it in this way. That means what? So when we are wearing socks and shoes, we do what? We first wear socks and then we wear shoes, right? But when we are opening them, we first open the shoes and then we open the socks, right? In the similar way, if we want to find the AB inverse, so the B comes first, what is the last that comes first, and what is first that comes last, okay? The next important property we have is the cancellation property. That means what? Suppose we have a group G and we have three elements in our group, that is A, B, C. Now, if we have in such a way that AB equal to AC, there or we have BA equal to CA, okay, then we can do what? The second element or the common element we can eliminate that and we get B equal to C. So for group, it is possible to have such a property. Okay, now we have what? Now the third property we have, suppose G is a group and we have two elements, that is A and B are two elements in G. Then they are saying that we will get element C such that, so we don't know whether what is the property or what is the relation between A and B, but if we take any two elements in the group G, we will always get element C such that if we take the binary operation of A with C, it will give us the element B. In a similar manner, we will get a element D such that if we take the left operation with the element A, it will give us B, okay? It doesn't necessarily means that these two elements has to be equal, okay? Now let's move to the next page. Okay, so now here we have the definition of order. So order of a group is very easy. So if you want to define the order of a group, it is nothing but the number of elements are there in the group G. So if we are having three elements in the group, we have the order to be 3. But if we have seen the S3 is what we have seen. It is the permutation on the group of on the elements 1, 2, 3. We have seen that this S3 has 6 elements. So from here we can say that the order of S3 is 6. Okay. And there's one more thing we have, that if the group has finite number of elements, that group is known as finite group. And if it has infinite number of elements, then that case the group will be known as infinite group. Okay. Now suppose we have G is equal to Z5 and the order of G is equal to 5. Okay. That means what? In G5 we know that how many elements do we have in G5? We have 0, 1, 2, 3, 4. So in G, we are having 5 elements. So from there, we can say that the order of G is 5. And hence, we can say that G is a finite group. On the other hand, if we talk about Z, it has an infinite group because we are having infinite number of elements in that group, right? Okay. Now, if we talk about U20, U20 is what? It is the multiplication for Z20, and we are picking all the elements from Z20 such that the GCD of that element with 20 is equal to 1. So the elements of U20 will be what? It will be 1. 2 GCD of 2 and 20 is not 1, it's 10. And then we have 3 because GCD of 2 and 3 and 20 is 1. Then we have 5. No, 5 is not there. 6. 7 is there because GCD of 7 and 20 is 1. And then we have 8. 8 GCD of 8 and 20 is not 1. 8, 9. 9 will also be there. 10 will not be there. 11. 12 will not be there. 13. 14 will not be there. 15 will not be there. 17. And then we have 19. So how many elements do we have in U20? 1, 2, 3, 4, 5, 6, 7, 8. So from here we can say that the order of U20 is equal to 1. But what happens if we want to find the order of an element? So in group, when we are defining a group, we can define order in 2 ways. First, we have the order of group. So the order of group is very easy. It is the number of elements. In this, we have having 7 elements. So the order of U20 will be 7. But first, say if you want to find the order of an element, first say A belongs to U20. And if you want to find the order of the element, we find the least possible number, or we want to find the least number n such that it gives A to the power n equal to identity, right? So E is also known as identity. Now suppose this element 7 belongs to U20 and we want to find the order of 7. So first we start with smallest number we possibly can. We first find 7 cube. So 7 cube is 3. So if we want to find 7 minus 3, we have 3 into 7 is 1. So from here we get it to be 7. Okay. So this is how we can find the order of an element. Now let's move to the next one. That's all for today. In the next class, we will talk about a few of the basic properties of order, and then we will move on to the basic things that we can define using order. Okay, thank you for this one.